Hi there. What you're seeing here is a divide and conquer Monte Carlo tree search in action. This is a planning algorithm that plans in a kind of an unconventional fashion. So we're going to explore this today in this paper, Divide and Conquer Monte Carlo Tree Search for Goal-Directed Planning by Giambattista Parascondolo and Lars Büsing and a list of other authors. And I believe this is from DeepMind and Max Planck and ETA, and yeah, that's it. All right, so what does this thing do? It is a planning algorithm, and planning might be not really familiar for you. So let's say you are in this room or this set of rooms right here. There's a bunch of walls, and you are up here, and you want to reach the goal down here. So first of all, this is a goal-directed problem, right? Here it says goal-directed. Goal-directed means that you give the algorithm a goal to reach. And this could be a different goal each time you run the algorithm, right? So you give it a goal to reach. Then the second thing here we see is planning. So it is a planning algorithm. What does planning mean? Planning means if you're traditionally reinforcement learning, you would think, I'm just gonna go ahead and run my agent here, and maybe you can move in the 4 different directions, run my agent here, do some things, right, blah, 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 blah. Maybe I hit a wall, I get a negative reward, I try again. In planning, you don't have to move initially. What you can do is think about moving, and you can think ahead of what's going to happen. And that's usually because you have some sort of model what happens. This is very famous applied in, for example, AlphaGo or AlphaZero, where you know, if I move to the right here, I'm going to be here, right? So you will know once you've reached the goal, right? If I'm here, I go down, I reach the goal. Cool. So you can think all of this without actually moving in the environment. You can think yourself ahead. What would happen if I did certain things? And that in turn also means that you can think ahead multiple different paths. So you can think ahead what would happen if I move right, what would happen if I move down. And then you can think in the next layer, if I move right, what would happen if I moved right again? What would happen if I moved down instead? So you can easily see the planning problem becomes a tree search problem. In this case, we've done a breadth first search, right? And eventually you'll see that this will get you to the goal. So this breadth first search, or maybe you want to employ a depth first search, will ultimately get you to the goal. We can represent this as a search tree. So you're here in a particular state and you have a bunch of actions. In this case, 4 to move left, up, down, or right. And you can choose any of them and you will get into a new state. And from each of those, you could choose any again. And you can think ahead all of this. You can construct this entire tree. And one of these branches will lead you to the goal. Promise. What is the problem? The problem is if the path to the goal here is, let's say, D steps long, then this tree here is going to be D layers deep. And in our case, that means we'll have 4 to the D nodes in that tree before we even reach the goal. And that is just a long, or a big tree. And we can't construct all of it. So algorithms have come along, for example, the A-star algorithm, where you can incorporate something like a heuristic. And the heuristic would be, well, it's generally good if I'm close to the goal in L2 distance. So you would not build the entire tree here, but you would prefer nodes that will bring you towards this heuristic. So this node down here is closer to the green node in terms of L2 distance, and this node down here is even closer, but then you're kind of stuck. So A-star will explore a bit, probably along this wall here. And once you're here, you have a clear path again, right? So you can simply take the actions that minimize this L2 distance. So this will already get you to a real good point. Monte Carlo tree search, as it was employed in AlphaGo or AlphaStar, has a similar structure where it, after a certain while, it stops and it evaluates a heuristic to say what's the value here and so on. So it is, for some problems, an even better method of constructing the search tree in a way where you don't get overblown by the number. So the Monte Carlo search tree in this algorithm refers to the fact that we are generalizing Monte Carlo tree search from the, let's say, the AlphaGo paper. So what's the idea here? So far, we've known everything. The idea is the following. If I had an oracle, if I am the master here, and I can tell the agent, look, I guarantee you that this state right here in the middle, you will pass that state. If you want to reach the goal, you will pass this, for sure. If I tell this to the agent, now what can the agent do? The agent could say, oh, okay, if I know that, I don't have to search for a way to the goal. I'd much rather search for a way from my start point to that point where I know that I'm guaranteed to be at some place. And then I can search also from a way from there to the goal, right? So this now, remember our path was d steps long for the original problem. This is now, let's say, d half long, each of these paths. And that means we just construct two trees. Each one of them is going to be 4 to the d half, and the other one is also 4 to the d half. And if we add them, that is much smaller than the original 4 to the d tree that we build. So right there, we have subdivided our problem into 2 sub-problems, and each of them are much easier than the original problem. This paper basically does this recursively. So it will subdivide the problem by proposing some middle state where you are going to be at some point, for sure. And that for sure we're going to take a look at. And then for each of those problems, again, it will try to subdivide it into sub-problems and therefore recursively solve these sub-problems until they're small enough that they can be basically solved in one step. So that's the big idea here. And this is illustrated in this point right here. So you are in this S0, the start state, and you want to go to this S infinity, the goal state in your case. What this paper does is it proposes to split the problem here in the middle and then simply solve the 2 problems recursively. Now, what is a bit confusing right here is that it is the planning already is a tree search, right? So a plan is like a tree, but we are searching over plan. So we're searching for the best plan, which means that we are searching over trees, and that search itself is a tree search. So the search itself is a problem where we go down one route and then, oh no, and then we maybe go down another route and here and then here. So the search is a tree. So we're now tree searching over trees. That's the kind of tricky thing to remember. So each of these plans, even if it's only half done, like this is only half a plan, we don't know what's going to happen in here. This half a plan is a node in the tree that we're searching over. And then it splits, as you can see here, into 2 sub-problems. The 2 sub-problems also are nodes in that search tree. So you see that this top thing here would correspond to this node, even though in itself it is a plan, a tree, a string in this case. And each of the 2 sub-problems would become these nodes in the search tree. So keep that in mind as we go through this paper. It is very easy to get confused in this respect. The algorithm is pretty simple in this case. So this algorithm rests on this traverse procedure. So we're going to traverse this, what they call these OR nodes. So they divide the problem into AND nodes and OR nodes. I don't believe that's particularly necessary for us to think about, but here's how this works. So they traverse the OR node S to S prime. This is simply, again, this is a node, but the node is a path from S to S prime, where we don't know yet what happens in between, right? So what we'll do is we'll run this procedure here, select. And select, you can see it outputs an S prime. And the S prime is going to be a node here somewhere in the middle, where the model says this is your subdivision point. And then it will recursively traverse the left and the right branch of this tree. So it will subdivide the problem into two problems and then recursively call this traverse. You see that's the function that we're defining. Call this traverse function on these. So it will subdivide this problem into these problems, and for the next step, again, it will for each of the problems propose a middle node and subdivide it further, and so on, until you have a full plan, right? At some point, you're going to have a full plan. Now, here again is the important thing to remember. This is just one branch of the search. This is just one possible plan. And we are going to do a tree search over these plans. So this select function here, it has returned this S prime, but it could have returned any point between S and S double prime. So this is just one branch. I don't have space to draw here, but I'm going to draw it down here again. So it could have also returned this particular node here, like it's a different S prime, and then subdivided the problem into different problems. And then, of course, those problems are now different, so they would be subdivided differently again, and so on. So this top part here is just, if you consider this thing here, your root node, this is where you search from. This top part is just one node, one branch in the tree, but we could also subdivide like this, and then that would be another branch in your tree. And this tree here is the thing that you're searching over. So important to keep this in mind. We're searching over these different possibilities. Now the rest of this algorithm here is basically the carryover from Monte Carlo Tree Search. And I don't want to go into that in this video, but if you're interested in how to actually implement this, you'll have to go look at MCTS, and then all of this just carries over from that algorithm, because you have to keep estimates of value and visit counts in this tree and so on. And also you have some sort of a value estimator. But yeah, I'm mainly concerned with how the tree is constructed right here. So basically, here's the difference between the Monte Carlo Tree Search and the divide and conquer Monte Carlo Tree Search. In Monte Carlo Tree Search, ignore the yellow one for now. You're in the green position, and you want to go to the blue position. In Monte Carlo Tree Search, what you're searching over is the next action to take. In this case, you have 4 possible actions to take. And that's what you're searching over, and that's what you build your search tree from. Your search tree is going to be which action to take, right? Up, left, down, or right. That's why you have 4 actions. In divide and conquer Monte Carlo Tree Search, you're not searching over actions. You are searching over the best way to subdivide this problem, right? You're searching over which of these, all the black squares, should I use to subdivide my problem into sub-problems. And that's what you build your search tree from. So naturally, you can already see what kind of possibilities do we have here to subdivide this problem. I drew one white square, but any of the black squares are candidates to subdivide this problem, right? Any of the black squares could be potential subdivisions. And this is what we search over. So in Monte Carlo Tree Search, we search over the actions, which gives us this 4 to the D tree. But in divide and conquer, we're searching over all the ways to subdivide the problem. And as you can see there, that are many, many more possibilities. So from this first starting node, we have like 100 possibilities to subdivide this problem into 2 problems, right? And each of those, again, if you've decided on a subdivision, let's say you decided on this one right here. You say, I want to pass through that point on my way to the goal. Now you have to subdivide that in this sub-problem into 2 problems. Again, every possible black square. I'm not saying which one is a good thing to subdivide the problem. I'm just asking what is a possible candidate. Every single black square here is a possible candidate for a path from here to here. Right? And again, for this particular subproblem, you have to do the same thing. So the search tree here, even though we said before, this one is very deep, and this one is probably only log d, so log 2d deep, its width is going to be enormous. And that is the catch. Right, the catch. This is not a method that is like a magic pill. The catch is, even though your tree is not as deep, it is much, much wider. And it is intuitive, right? Because you still have to have the ability to construct any possible plan. So your tree is going to have as many nodes as the original Monte Carlo Tree Search tree, if you were to fully expand it. Right, so you're trading off depth for width here. I hope that's a bit clear. So your entire promise of this method is going to be, can you, from all of these possibilities, so from all of these, you don't even want to go and search even one layer deep through all of these. You don't even want to consider all of them, right? You want to search in this tree, you want to limit your search to very particular ways of subdivision here. If you can do that efficiently, if you can pick efficiently candidates to subdivide, then this could be a successful thing, because your tree is not as deep as the original search tree would have been, and you can limit the width effectively to only very few candidates. So here we could, for example, make a heuristic that will always only pick squares that are kind of on this straight path to the goal. So everything rests on how you do this select action, this thing here. The entire algorithm relies on the fact that you can effectively select in between states where you're pretty sure that the algorithm will have to pass through there. Because the worse you make these predictions, the worse your tree search is going to work. And what they do, of course, is they use deep learning, as you might have guessed, to do that. So they will have a model that for a particular start and end goal will give them a probability distribution across candidates. Now, everything that's black here also has probability mass, but it's just so small you can't see. And these blue ones are the lighter blue, the more probable this model thinks that this is going to be an in-between state. Now, the tree search can now limit itself effectively to only the ones here with the highest probability, right? So we select the ones with the highest probability, and we'll only search plans that have these as the first possible subdivisions. Again, we're searching over plans, so we're searching over ways to subdivide the problem into smaller problems. That is our search space. So once we've decided on one of them, let's say here the yellow one, again, we have to evaluate that model for each of the sub-problems. And this is kind of a step that's missing here. So in between here, there would be a model evaluation that would, again, tell you which of these in-between states were probable subdivision candidates. And then you would select, again, one of those in that particular search branch. And in a different search branch, right? You're searching over these things. In a different search branch, you would select a different one and see, is this possibly a better way to subdivide the problem, and so on. So the question, of course, is how do you train this model? How do you train a model that gives you good candidates for subdivision? And the answer here is comes from the idea of hindsight experience replay. So let's say, again, you are here and you want to go here, and you're not very good at it initially. So they train this model, as I understand, along with letting their agent act in this environment. So the agent uses the model to plan, but initially it's not very good. So maybe the agent will fail a lot of times. So instead of going to the blue square, it will reach this white square right here. It will go here, here, and here. We'll reach the white square. And instead of saying, oh, I failed, what you can do, and this is the idea of hindsight experience replay, is to say, well, I did fail, but I did reach something, right? I have reached a thing. And it's actually possible that that thing could have been the goal, but this particular episode, this was the goal. Remember, the goal changes every time. It's a goal-directed policy. So it says, well, this could have been the goal, possibly. So if I just pretend this was the goal, then I have a training example for a successful run. So the hindsight experience replay basically pretends that what you have achieved, even if you failed, was your actual goal, and that gives you a positive training example for an episode with that as a goal. And it could have been the goal because the goal is chosen at random. So this gives you a good training example. Now this paper just generalizes the hindsight experience replay or applies it to their particular framework, and they say, well, if I reach this thing, that means any point on this path is a good candidate for subdividing the path because I did actually reach the point. Remember, the goal is to propose a point where you're for sure are going to pass through. Now, since I've taken this path to this goal, I have passed through any of the squares in between, and so these are my possible sub-candidates. And all other black squares, I don't want that. So now I have a classifier I can train. I can say any of these squares on my path are good squares to subdivide, and any not on my path are bad ones. They go a step further, I believe, and they actually say, so if this was m steps, we're actually going to take the particular square that is reached after m half steps. So the exact middle point of that path is going to be our training example for subdivision. So you have a classifier that has exactly one target to train. So this you train along with acting in the environment, and of course your model for proposing subdivisions is going to be better and better and better and better, and that makes your planning algorithm better and better, and that makes you collect better episodes, and so you can sort of bootstrap yourself up this thing. Now, this is the basic experiment of the paper. They also do this in a 3D manner where they move this little spider here around. So the spider was trained to just move from one block to the next block, and the planner basically has to tell it where to go. And they show that they outperform the traditional Monte Carlo tree search. Now, I have to say, this is cool, but you have to remember this is only advantageous in very, very specific types of problems. So first of all, it has to be this goal-directed nature. Otherwise, you probably couldn't train this this predictor here super well. Then, given that you have such a good predictor, the problem needs to be such that if you have a start state, there could be many ways to go about reaching the end. And if you have an end state, there could be many ways from where you could come from. But there is like some bottleneck state in the middle where you're pretty sure that you're going to have to pass through it. So if your problem is of that nature, right? If it has these bottleneck states where you can predict with reasonable accuracy that you're going to have to pass through, then this is a good algorithm to consider, and is obviously, I mean, it's intuitively outperforming the original Monte Carlo tree search, because you have much less deep search tree and you can effectively limit its width by using that model. They also have made this website where they kind of show videos of their spider, and I haven't seen it in a while, but it is like next to the mouse, if you can see it. So so you see, this is kind of a continuous control problem that also requires planning. And they also have these kind of GIFs of how what order their plans are constructed in. So I invite you to check this out, read the paper. If you like this, subscribe, leave a like, leave a comment, and thank you for listening. Bye-bye.